third session of the topologically protected spin textures, fundamentals and applications. So we have two invited speakers and one contributed speakers. So we had a small program change. So the first speaker will be Mathias Kläui, and he will be speaking about current-driven, skyrmions, and I think I let you.
So firstly, let me thank the organizers of course, Sean, for organizing this exciting session. Thanks to Stefania for swapping. That relaxes everyone in the room. All right, so I'm going to talk today not just about fundamentals, but really also about possible applications. And after some very brief introduction, because you all know what's going on, you're all super excited, I'm actually going to talk about applications to non-conventional logic. Everyone knows the racetrack, but I used to work for IBM. I sold all my shares in IBM, so I have no vested interest. But I also, since the last 15 years, every year I've been saying the racetrack is 5 years from market. And so I'm giving up on that now, so now we're going into non-conventional logic. But first, let's start. So what do we need in order to make skyrmions stable? And for that, we need a special interaction. So we all know the spin-spin Heisenberg exchange interaction, which stabilizes spins parallel or anti-parallel. However, it doesn't care if the spins couple like this or like that or like that, so there is no predefined chirality. However, that's a problem because it means that these two types of domain walls, these two Niel domain walls with clockwise or counterclockwise rotation, have the same energy, and that means they can actually annihilate, and that means they're not topologically stabilized pairs of those. So what do we need in order to make one of these domain walls stable and the other one not? And for that, nature has something in store for us, which is the Dzyaloshinskii-Moriya interaction, which couples at the interface between a heavy metal and a ferromagnet two spins, not just parallel or anti-parallel, but actually perpendicular. And not just perpendicular in any direction, but only one perpendicular orientation. And that means that you have a fixed chirality when the spins cant from left to right. So here we see a clockwise. Yeah, now I think it works. Okay, great, thanks. So I'm not going to repeat everything, but for the online people, please read these 2 papers. They're amazing, and you'll learn everything about orbital currents and the Orbital Rashba Edelstein Effect, and it gives you 16 times larger orbital torques, and everyone's happy. Okay, good. But now we want to move skyrmions with it. And so here is what the student that was working on that drew before he did the experiment. He put 4 skyrmions on a racetrack, inject currents, move everything, and then build a device. Now this is what it looks like in reality. We have 4 skyrmions. We're super happy. But when we inject current, we see that these 4 skyrmions, well, they kind of move, but they don't all do the same. And initially we start with 5 skyrmions, and then after some time we are left with 3 skyrmions, so we lost half of our data. So this is not good. So, IBM was not impressed. So the question is, why do those skyrmions not do all the same thing? Where does this pinning come from? So that's something which we spent quite some time investigating. And what we did is we looked at a sample and we determined the energy landscape of a sample. And red spots are pinning sites, and black spots are areas where the sample never goes. So from this, we can actually determine the energy landscape. You see it's rough. It's not flat. So skyrmions like to sit in certain positions, and they are repelled from other positions. So we can calculate the energy landscape. And now we want to understand how a specific pinning site pins a skyrmion. So what is the origin of the pinning? And for that, what we did is we looked at the skyrmion here, and we see it doesn't randomly move, but it moves between certain positions where it likes to sit. And we then actually plot the circumference of the skyrmion for these different positions where it likes to sit. And then we see that the domain wall here for the black, for the red, for the green, or for the blue, the domain walls, they superimpose for large areas, meaning that there are areas where the domain wall likes to sit. And it turns out it is not the center of the skyrmion which is being pinned, it is the domain walls. And that's also something that we can understand because the domain wall is where the exchange energy is highest. So obviously, if the domain wall can lower its energy by sitting at a position where the DMI or the exchange is a bit lower, this will actually save it a lot of energy. So it turns out that we can actually understand the pinning of the skyrmions by the pinning of the domain walls. And that's kind of nice because this allows us also to tune the skyrmion size by pinning one end of the skyrmion and moving the other side of the domain wall a little bit. And this gives us a lot of flexibility for tuning the energy landscape of the skyrmion. If you're interested, the paper just came out a couple of weeks. Okay, yeah, and we also saw that the same is for a stripe domain, not just for a skyrmion. Also, the domain walls of the stripe domains like to sit in the same position where the domain walls of the skyrmions like to sit. Okay, good. So now, if we crank up the power, we can overcome pinning. And then we can get reproducible domain wall motion. This was shown already a few years ago, where we saw that the skyrmions can move reproducibly 10 billion times back and forth, and then IBM was happy again. The skyrmion velocity tracks the pulse shape very nicely. However, we also see that not just the skyrmions move along in the current flow direction, but also, and now I need to wait until the computer has decided to go to the next slide. That the current and the skyrmions don't move parallel, but under this so-called skyrmion Hall angle. And that was something that was investigated actually by the group of Axel Hoffman and us at the same time. And we found that the skyrmion Hall angle, in contrast to theory, actually has a dependence on the velocity. Theory predicts it should just be flat, just depending on the size. But here it seems to change with the velocity. And we had experimentally similar results, but completely different theory. So in their work, the Charles Reichert family, Cynthia Reichert, they predicted it's due to pinning. We predicted it's due to spin structure deformations. And in the end, it turned out that both were right. Their theory holds in the creep regime. Our theory holds in the viscous flow regime. And then, meanwhile, there's quite a bit of literature on this, including a recent work that we did, where we showed that depending on the regime of the dynamics, the change of the skyrmion Hall angle with velocity actually has different slopes. All right, so now we can move the skyrmions in the racetrack, but the question is, of course, why has no one built a racetrack commercially? Well, there are many reasons. There's a big reason, and that is market. There's already pretty good memory out there, and you'd actually have to compete with that. So we went away from skyrmion racetrack and went to non-conventional computing using thermodynamics. So your brain is a good object that uses thermal dynamics. So your brain operates at the very threshold at stability. Your brain has a lot of mistakes that happen all the time, and sometimes you see that with me. But so you have a lot of activity in your brain which is not deterministic, but it's stochastic because your brain doesn't want to use more energy than absolutely necessary. And so we will do the same. We use thermal diffusion, so dynamics of skyrmions in this multilayer here. And when we move it, we see that the skyrmions not only move in the current flow, but they also wiggle around. So this is a signature of Brownian motion dynamics, like a blue ink in water wiggles around. Here our skyrmions wiggle around. Now this was theoretically predicted to be wrong. So theory predicted here in this paper that this should not be observable. So we were a bit skeptical, but then I told the student just switch off the current, switch off the field, and just observe. And this is what you see. The skyrmions don't sit still. They actually move around by Brownian motion, as you can see here. And this Brownian motion moves them randomly in this energy landscape. And if you then plot the mean square displacement as a function of time, it's completely linear, and that means it's diffusion. It's pure diffusion. So it's not super diffusive, it's not subdiffusive, but it's pure diffusion. And this was actually reproduced by Uli Novak. The paper came out a couple of years ago, and there's also some other work by our colleagues. But we got excited because when we started this work, and we said, well, forget about the racetrack because this diffusion is bad for the racetrack, our colleagues, Daniele Pinna, Karin Everscher-Sitte, they wrote theory papers about using this in stochastic and reservoir computing. And that's how we started. 3 years ago, I had no clue what all this stochastic, reservoir, neuromorphic, blah, blah is. I still don't have much of a clue, but I got more excited about it. So what can we do in order to make use of this thermal dynamics? So the first thing we need to have very fast thermal dynamics. And in order to get very fast thermal dynamics, we actually teamed up with Uli Novak on synthetic antiferromagnets. And we found that if you have a topologically trivial combination of two antiferromagnetically coupled skyrmions, they can move 10 times faster than ferromagnetic skyrmions. So actually we have a 20 times increase of the diffusion. And if you're interested, here is the paper on archive. If you're a referee, please be kind. So we can do very fast skyrmion dynamics due to random diffusion. But let's use it. So here let's start with non-conventional logic using skyrmions. So first we're going to use stochastic computing. So stochastic computing is a non-arithmetic way of calculation using random bit streams. It's an approximative approach, and it's a simple way of multiplying numbers, and you can do also scaled addition. But there's a problem, and that is the creation of unbiased, uncorrelated bit streams. Now this sounds very cryptic, so let me explain this to you. So if you have a coin, you flip the coin, you have 50% chance of heads and tails. If you have 4 cards, the chances of an ace is 25%. To encode the information of 0.5, we actually encode this in a bit stream where we have 50% ones and 50% zeros. So 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0 corresponds to 0.5. And 0.25, you have 25% ones and 75% zeros. So 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, and so on. That corresponds to 0.25. So in a bit stream, we can actually encode any information between 0 and 1, any number between 0 and 1. So now we will use these 2 bit streams and feed them together in an AND gate. And then what we get out, 0 and 0 is 0, 1 and 0 is 0, 0, 0, 0, 0, 0, 1 and 1 is 1, and so on. Then we get a number out of this AND gate, and it turns out that the number we get out is actually the multiplication. So the bit stream that is coming out of the AND gate is actually the multiplication of 0.5 and 0.25. So 0.5 times 0.25 is 0.125. So the chances is 12.5% to have both heads and an ace. So this means if you have these bit streams, you can very efficiently generate a multiplication of the 2 numbers. Now what's the problem? The problem is the bit streams x and y have to be uncorrelated. So let me show you what this means. So here we have a bit stream that corresponds to 6 over 8. 1, 1, 0, 1, 0, 1, 1, 1. So we have 6 over 8, meaning 6 ones and 2 zeros. Here we have a bit stream that corresponds to 1 half. We have 50% ones and 50% zeros. And if we do the AND gate, 1 and 1 is 1, 1 and 1 is 1, 0, we get this one here, which is 3 over 8. That's completely correct. Half of 6 over 8 is 3 over 8. Now, we put in two identical bit streams, so fully correlated. And 6 over 8 times 6 over 8 is not 6 over 8. So that's definitely wrong. So completely correlated input streams give you wrong results. And so now what we have to do is we need to shuffle around the order of the ones and zeros while keeping the number of ones and zeros constant. So to reshuffle the order of the ones and zeros to decorrelate these input streams. And there is no efficient, scalable, low-power solution for this using CMOS. And that's where we set in. We need a way to reshuffle the order of the ones and zeros while keeping the number of ones and zeros constant. Okay, and this is what we built. We built a reshuffler made of two chambers. Up here is a 1, down here is a 0. If we inject here a skyrmion, it's a logic 1. If we inject here a skyrmion, it's a logic 0. If the skyrmion exits here, it's a logic 1. If the skyrmion exits here, it's a logic 0. So we nucleate here with currents. We do readout by imaging or by TMR devices, and then we look at the input and output. And what we see is, so here skyrmion enters is a logic 0, and here one enters a logic 0, here one enters a logic 0. Now one skyrmion exits here, it's a logic 0. Another skyrmion exits here, it's another logic 0. Now a skyrmion exits here, it's a logic 1, and so on. So now we have here an input stream and here an output stream. And because the skyrmions are actually not getting lost, they're topologically stabilized, this means that the number of ones entering here and exiting here is the same as the number of zeros entering here and exiting here. So there's no 1 and no 0 is lost, but because they move around here randomly, the order of which the skyrmions enter here, exit here, exit here has changed. And you see the skyrmion bit streams, input and output, look very different. And if you calculate the p-value change, it's negligible, meaning that all the skyrmions that enter here, exit here, all the skyrmions enter here, exit here, so no skyrmion got lost, but the correlation is down to 11%. So that's really good. We've nearly completely decorrelated the input stream into an output stream while keeping the total number, i.e. the represented value, the same. And we, of course, tried to make the cover page of Nature Nanotechnology, and we failed, so you get to see this instead. And now you can feed these streams into an AND gate, and then you can have a probabilistic computing that does very efficient and very low power multiplication. And now in the last 3 minutes, let me show you another more recent approach, reservoir computing. The problem with these very nice stochastic computing is that we can only do very few operations very well. We can do multiplication and scaled addition, but it's not a general purpose computer. Reservoir computing is pretty exciting. Reservoir computing is something that for pattern recognition is a very topical area of research because it maps a complex problem into a linearly solvable one. So it comprises an input, a reservoir, and an output. And then the network that we use here does not need tuning, so the connections inside, they don't need tuning. We only tune the output. So there's no problem with training. And what it does, it projects, for instance, this ensemble of these blobs into a higher dimensional space where they can be easily be separated into these different classifications. And of course, there are different ways to realize this, and we have chosen skyrmion fabrics. Actually, all the honor to George Buriano from Intel, who came up with this together with Karin Everscher-Sitte. And here's a paper where we conceptually suggested that. So we have our input. They go as current into a skyrmion lattice, and then, or a skyrmion fabric, and then we have TMR output junctions. And now here is the simplest version of it. We have here our skyrmion lattice, and we have 3 inputs, which can be put to plus, minus, or 0. And then we actually look at the position of our skyrmions for different combinations of inputs, and we read out the skyrmion in 4 different positions by, for instance, TMR junctions. And then as a first approach, we simply showed whether it can do Boolean logic. And we see, for instance, AND works very well, NAND works well, OR, NOR, XOR, and XNOR. And the interesting thing is that XNOR is actually a non-separable function, so that cannot be realized with a simple perceptron feed-forward network. So that's something that was very exciting because it allows us to actually outperform a simple perceptron just using a single skyrmion in our reservoir. If you're interested, the paper is coming out in a couple of weeks. All right, so this is the end of the presentation. Most importantly, this is the people that did the work before Corona, during Corona, and after Corona. And we have great collaborations at MIT, Konstanz, LBL, PSI, at the MPI in Stuttgart, in theory in Mainz, as well as our 3D Magic Consortium and Christian Gut in Siegen and colleagues in Zendai in Sydney. Nothing would work without funding, in particular the RSC Synergy Grant. And then to summarize, DMI stabilizes chiral spin structures with a defined topology. We find that pinning is at domain walls. Here are the papers. Skyrmion motion can be obtained due to spin orbit, but in particular orbital torques. We get the Skyrmion Hall angle and very efficient dynamics. We get this thermally induced Skyrmion diffusion, in particular in synthetic antiferromagnets that can be used for probabilistic logic. And we've realized low-power reservoir computing. If you're interested, there are all the papers. If you're new to the field, there are some reviews. I'm very happy to share the slides, so if you don't want to write down all the references, send me an email. We also have open positions for PhD students and postdocs. And with that, I thank you for your attention.
Thank you, Mathias, for this comprehensive talk. Are there any questions in the audience? Yes. One moment, please, for the microphone.
A second.
The Skyrmion Hall effect.
People live in real life, not just 2D. Yeah, go ahead.
I'm saying that the Skyrmion Hall effect created the problem in long propagation in the waveguide.
Yeah.
Was it possible to find the solution of the problem?
Yeah, I think there are two solutions that we at least are exploring. I mean, we saw one in the talk before using these anti-skyrmions and then choosing the right angle, but I think that's quite tough. So what we use is synthetic antiferromagnets. Synthetic antiferromagnets, you have two skyrmions which are coupled, and since they want to go in opposite directions but they're coupled, they go straight.
So the answer is the antiferromagnetic skyrmion.
I think that's one answer. That's the one we are doing like right now. So synthetic antiferromagnetic skyrmions, yeah.
But do you believe in the future for the skyrmionic racetrack?
Is anyone recording this? I can tell, I said this in the beginning. When I left IBM, I sold all my shares in IBM, so I have no vested interest. That's all I can say about this.
Yeah, thanks, Mathias. For the reshuffling problem, so you need to conserve the skyrmions, but it's known that when you drive the skyrmions with current, sometimes it happens that they annihilate each other. So how do you control these in your devices?
Yes, it's a good question. I didn't talk about this in a lot of detail. So it turns out that in the skyrmion reshuffler, we find that they never annihilate. And the reason is that we have very little pinning sites. It's an optimized stack. And the skyrmions that we're annihilating, they only annihilate if they're pinned, because then they're not topologically stabilized anymore because DMI is low. So here, we find they play billiard. So they actually interact. If one goes close to the other, it is pushed away. And you see here, so the p-value change of 0 means that no skyrmion is lost. So we put like 10 to the 6 skyrmions, and 10 to the 6 skyrmions come out. So by engineering this, you can make it so stable that actually this problem of annihilation is not there. I mean, it's not so important anymore that the skyrmions actually get annihilated. So I think we can make them stable over years with no visible decay.
Okay, Kai.
Very nice talk, Matthias. For the pinning you mentioned, how much does that depend on the skyrmion size? Because the proportion of the domain wall will be different depending on the size, for example, right?
That was me. Okay, so the pinning depends very strongly on the skyrmion size, and we now have a paper on arXiv where we show that if we actually have an AC field excitation that changes the size of the skyrmion periodically, we can get rid of all the pinning. Because the pinning only works for a certain size. A certain pinning site only works a certain size. If you periodically change the size, as soon as the skyrmion enters at a pinning position, already has changed its size, it's not pinned anymore.
Right.
And then it's fully diffusive and a flat energy landscape.
And this pinning is from whatever defects?
Yeah, it's a
in-
polycrystalline film, so we think it has to do with grain boundaries, because that kind of fits also the size. But it's, I mean, if for the students, if you want to make a huge impact, find out where the stupid pinning is coming from. It's a very tricky question, but it would be really good if you figured out. We don't know. We think it's grain boundaries where the DMI is changing.
Thank you.
I have a follow-up question to Saul, actually. When you showed this...
Can you go full screen again? I'm sorry, I pressed on the wrong button. Oh, wow. And now I
computer
crashed
is
the
thinking.
computer.
Actually, yes. So here you are generating skyrmions and you're moving them by injecting some current,
Yes.
I suppose.
Yeah.
So you are you rely on the fact that the skyrmion will not be linear with the current, because otherwise you cannot generate that stochasticity.
Ah, yeah, okay. So the stochasticity comes from just thermal activation, and we can use extremely low current density of 10 to the 7 amps per square meter, because we have this additional thermal activation. And so indeed here there's a superposition of drift due to the current and diffusion due to random thermal activation.
Okay.
So this superposition means that eventually they move, but they don't move exactly with a predictable deterministic velocity. So that's why you have the reshuffling in this chamber here that leads to this order of the skyrmions exiting being different from the order of the skyrmions entering. So you have both a small current pushing it, but on top of that thermal activation that moves it in a random orientation.
But the operation will be very slow then.
Absolutely. So there's no free lunch. So low power typically comes with low performance. I mean, the application we have in mind is autonomous sensing, where you need very little logic, but you have very little power available. So we work with companies that do autonomous sensors, which rely on energy harvesting, and they only need very simple gates, AND gate, OR gate, majority gate, and things like that, which you can use here. And they only need power, they only need performance where they need calculations in the hertz range. They don't need gigahertz. Like for a sensor, you're not going to read it out at gigahertz speed, but you're going to read it out once a minute. A CO2 sensor to see if people have enough oxygen, that's something you read out once a minute. So it can be very slow, but has to be very low power. So that's absolutely. So we don't try to compete with Intel on making Pentium processors.
Okay, thank you. Okay, is there any other question?
Yeah,
Yes.
sorry, just a quick curiosity. I didn't read your paper. So is that a synthetic antiferromagnet?
So this was actually shown in a normal ferromagnet, but
Because I don't see any skyrmion Hall effect, so they seem to be all, on average, to go straight.
yes, because they're very large. So the skyrmion Hall angle is 18 degrees or 13 degrees. It's very small. The skyrmion Hall angle for these large skyrmions is very small. That's why we don't see it. But in the other one, it doesn't matter. In the synthetic antiferromagnet, they go straight automatically for free, and they go faster. So they're really good. But we just did that a couple of months ago, so that's why we're not there yet to do it also in devices. Hi.
Okay, thank you, Matthias. So we have to move on. So let's thank Matthias again.